So thanks for attending this lecture 4.2 regarding the heat capacities of the lattice, where we will essentially derive the Debye model, which was historically the first model that correctly took into account the quantum mechanical nature of solids and then predicted pretty well the heat capacities of different solids. So we will introduce first in this lecture the historical motivation for development of the Debye model that can be used to calculate the heat capacities of the solids. And then we will introduce to you the Debye model. And first, we will there estimate the mean energy of the system. So recall we are dealing with coupled oscillators here in our treatment regarding lattice vibrations. And then we will need to define or use the concept of density of states in order to proceed with the calculation. And we will now use the earlier found dispersion relation for the system. So we do not change the system from what we have already derived in our section 4.1. And this really helps, especially when we simplify the dispersion relation a little bit to actually perform the calculations. So this is what we will do during this lecture, and I hope you enjoy it. So I will now get started with the actual business at hand. So if we think of the history, is that the successful explanation of the heat capacity of the solid strengthened really the trust in quantum mechanics. And this is really what happened, that the back in the days, in the early of 20th century, so 1900 something. And many theories and models were developed in order to understand how the heat capacities emerge. And I guess it must have been pretty difficult at that time to try to understand what happens, because the models based on harmonic oscillators, they seem to work quite well with gases, and the approach seemed to work quite well, that when you had different rotational states associated with molecules and possibly different vibrational states, this approach and then the subsequent extension of gaseous molecules to be treated as a gas, as a kind of a freely moving mixture of molecules in order to calculate the heat capacity of the gas, like that seemed to work quite nicely. And in fact, even the temperature dependence of the system seemed to agree quite nicely with the relatively simple model. That when you cooled the system, certain energy states, for example, the vibrational states first, they will become frozen so that you cannot store energy into them anymore. You just don't have that amount of energies that you could statistically raise your molecules into these vibrational states, that you just don't have that kind of thermal energy anymore in the system, so that they will be more in the ground vibrational state. And then when you cool down the system even further, then eventually also the rotational states may become frozen up. And this, of course, affects the heat capacities of the gases, and that was being seen in the experiments. But somehow something happened when this treatment that seemed to quite nicely agree with all sorts of gases. And many different kind of gases can be studied, so that you can, for example, have even a monoatomic gas, a noble gas, and you may have gases that have slightly different shapes, so that also their vibrational states, like you may or may not have a variety of different kind of oscillation modes. And when you took that into account, like the approach worked quite nicely. But somehow, when one moved from a gaseous state of matter into the solid state, something got changed. And Einstein model was one of the starting points to help in reconciling the understanding. So many theories and models were developed And a good overview on that can be seen, for example, from the Hoffman's book, if you're interested in reading a little bit. And of course, from the internet archives, you can find plenty of materials. From the Wikipedia would be, for example, a good starting point. And here we will really focus on the first model that was successful at all, and this is known as the Debye model. And this is nice, it's intuitively understandable model, and it does pretty well already predict the high and low temperature behavior. It doesn't work that well in the medium temperature case, so close to the room temperatures, but I guess we just need to make some compromises here. So this is the motivation, the introduction for this section. Okay, like this is a big piece of physics from the historical point of view that really strengthened our trust in the quantum mechanics and this approach. And this is because of this, it's quite important to know and appreciate how is the Debye model and how it can be derived and how it works. But now let's without further ado, let's get started. So I will next try my best to explain to you what is a Debye model and derive it, so that we can actually understand and appreciate the subtlety involved. So earlier models that were used, they were either just purely classical, so for example the Dulong-Petit model that works at the higher temperatures quite nicely, or in principle quantum mechanical, such as the Einstein model, but the Einstein model is simplistic. So we only have not uncoupled harmonic oscillators side by side, and that doesn't really give rise to a dispersion relation in the phonon oscillations, and that actually affects into their predictions. And we will soon see that when those phonon oscillations and their dispersion relation is being taken into account in the model and in the calculation of heat capacities, things will be improved quite a bit. Dulong-Petit model agrees with the temperature, with experiments, and especially when we go to the higher temperatures. So that's the limit of applicability of Dulong-Petit model. And it really works for most of the solids. So that's the kind of a generic behavior of heat capacities for solids. An Einstein model works okay at high and at moderate temperatures, but really fails at the low temperature limit. So we know that there's something going on in our treatment that is not present in the Einstein model. And this is what Debye then went forward, and then he realized that if you really take properly into account the lattice vibrations, so phonons in your system, and then calculate heat capacity using the earlier approach, then we get a better agreement. So what we want to do, as always, when we want to calculate a heat capacity of a material, a system, heat capacity is defined via a derivative. So we need to calculate the mean energy, and then we need to see the change with respect to temperature. So the heat capacity is defined as the partial derivative of the mean energy with respect to temperature. And here E is the system's mean energy. And this is now what we must figure out. How do we calculate what is the mean energy? And this means, of course, that we must know all the ways the system can store energy. And this is what we have been looking at so far in our treatment. So in here we were interested in lattice vibrations. And when we want to calculate the mean energy, we really need to know what is the mean phonon state occupancy. So I'll just denote that with the L in the brackets. So L is my quantum number associated with the phonon energy. And we know that when we look into the energy of a coupled oscillator, earlier we found a relation, and now I have the energy. I have the subindex L there to denote that in principle L is a discretized quantum number, so that's why it's as a subindex and not as an argument of this function. And K seems to be more like a continuous variable, so that's why it's inside the parentheses. And this is of the form that looks very similar to the energy ladder of a uncoupled oscillator. So we have L plus 1 over 2 times the h bar omega, and now instead of like free space omega, we actually put in the dispersion relation of our phonons, so omega k here. And this is with what we proceed. And we now want to calculate what is the mean energy in this kind of energy distribution. So we need to kind of average or sum over the L's and K's. Average would be a better word here. And what we want to do is that we want to also average out a three-dimensional case. So here we must generalize our wave vector k from a scalar valued quantity into a vector valued quantity, and then we have 3 degrees of freedom in our case. So because of this, now we have 3 times, and then we have the mean value of our principal quantum number L associated with the phonon vibrations plus 1 over 2 times h bar omega k. And now, of course, the dispersion relation will be the dispersion relation of a three-dimensional material. So this is how we could calculate the mean energy. And now, when we look at the phonon number distribution and we are in thermal equilibrium, we know that this is governed by the Planck distribution. And L is now then, because of this, given by 1 over exponent of h bar omega divided by tau, where tau is the kBt value. So, and this minus 1. So tau equals the kBt. So this is how we can calculate the mean phonon number. And when we insert this into our previous equation for the mean energy of the system, we get that the mean energy, and now we are still having the k vector here as a variable. We need to somehow also average over that. We have 3 times, and we have the Planck distribution plus 1 over 2 times h bar omega. And we want to calculate the mean energy because we want to calculate the heat capacity, and then we want to calculate the partial derivative of mean energy with respect to temperature. So we don't really care about the latter 3 times h bar omega over 2 term, because that doesn't depend on the temperature. So please note this fraction here multiplied with 3 here, that doesn't matter here because in our treatment, because that doesn't really depend on the temperature. So that doesn't play a role in the formation of the heat capacity of the solid. So this is I hope it's obvious to you now. And now we have the mean energy, and that turns to be that it's 3 times h bar omega divided by exponent h bar per tau minus 1. So this is what we have, and still we have this as a function of k. And what we must do next is that we must sum over our possible k values in order to actually get the full mean energy of the system. And conceptually, what we should do here is that we should calculate a sum over states, because even though we have a very densely spaced k distribution, because the periodicity of our lattice is well, it's a dense lattice, so the k points are very, very densely spaced. So in principle, we should sum over the states, even though it seems to be like almost like a continuum of states. It is not. It's really a discrete variable, this k here. And what we should do is we should sum over the states over all the oscillators and directions and their degrees of freedom. So this is what we should do. And we would then end up in the full mean energy of our system. So we have the 3 times, and then we would sum over all of these different k components, because k is now really a 3-dimensional wave vector. So then we have this, what's left, we have the 3 times reduced Planck constant h bar times angular frequency k, and since we are dealing with a coupled oscillator system, we place the dispersion relation here instead of just the frequency. And then we have the 1 over exponent minus 1 from the Planck distribution. And I will ease up the notation. So instead of like a summing over kx, ky, and kz, I will just denote this kind of threefold summation of the tree tuple. So in fact, like this mathematicians would say that I get this is a tree tuple that the variable here describing k, so that they are actually like an ordered set of integers that describe me what are the values of kx, ky, and kz. Because remember, the amplitude of k is 2 pi over lambda, and then we have a discretized k. So in principle, we are describing the wave vector k using a set of 3 integers. And the integers, like their order, is not arbitrary, because a specific integer is related to kx, giving us the length or a strength of kx component, and another specific integer relates to the ky amplitude and kz. So in fact, these 3 integers is actually forming an ordered set, and mathematicians would say that when you have a bunch of n integers, they actually form an n-tuple variable. So here the mathematicians would say that this is a tree tuple. But I'm not a mathematician, so maybe I will just say that we would just sum over k values. This is a lot less clunky notation, but just please be warned that it might be not entirely always obvious to understand that what on earth is actually being summed over, because we are having a vector as the dummy variable we're actually summing over. So please remember that it's actually now 3 summations. So this is now how we would get the mean energy of our system. But the trouble is that this is a summation that it's not very easy to calculate. So I just say that it's non-trivial, which is a other way of saying that it's actually very hard to calculate. And how do we proceed is that we resort to some approximation. And how do we approximate things is that we assume now that k, although it is in principle discretized variable, we assume that it's actually a continuous variable. And this allows us to treat the math in a continuum limit, and then this summation can be turned into an integration over the variables. And this really helps, because then we can actually integrate this integrand here and proceed. And I have a footnote there that, okay, this similar shorthand notation for a threefold summation was already used when we were describing crystal structures, and that is right. So that I guess you are pretty familiar with this already. And we will keep on using this notation for summations also in the upcoming chapters, because we really are dealing with 3-dimensional solids here. So many times we need to sum over with these kind of variables. So, as I already mentioned, the sum over states now is being turned into an integral. And we want to integrate over the frequencies, so over the omegas. And since they depend on the k, that's fine. But we just need to change things a bit, so that instead of summing over k values, we now sum over the frequencies. And once we transfer our sum over states into an integration, like we get something that looks like, or we get exactly what looks like this. So we have it 3 times, and then we integrate from 0 frequency to a so-called omega d, which is the dpi frequency to be determined later. And then we must, because we are turning a summation into an integral, we must tweak the calculation a bit. So we must have the density of states here inside the integrand, and then we have the term that we were summing over previously. So we have the 3 times h bar omega divided by exponent h bar omega divided by tau, which was the kpt, and minus 1. And now we integrate over the frequencies. So here, d is our density of states of lattice vibrations, so the density of phononic states, and omega d is the dpi frequency that we will determine later based on the kind of variables we have here. So we will normalize, scale the integration later. And now our earlier problem has been turned into finding the limit of the integration. So basically finding the Debye frequency and of course the density of states. But we know that the density of states can be calculated because we do have a relation for the phonon distribution. So we have the dispersion relation of our system. And in general, please be warned or embrace yourself that the density of states is a very essential concept in condensed matter physics and in solid state physics. So this will be used all the time when we are making calculations. So if you are not exactly sure what happens here and why do we need to introduce a density of states when we are changing a summation into an integral, maybe you should recap what happened earlier when we first time introduced the density of states and kind of think about it, what happens here. And now, this is the first part, that we now have a functional form for the mean energy, and now what we do next is that we will first find out the density of states in a three-dimensional case, so that we will next find out what exactly is this form, and then we will proceed in making the calculation, finding out the Debye frequency, so that we can actually then get a functional form for the mean energy, and then we can calculate the heat capacities, since the heat capacity C was defined as the partial derivative of mean energy with respect to the temperature. So first, we want to calculate or find out a relation. How does the density of states look like in a three-dimensional system? And here we think that we have a system consisting of n cubed atoms, or more precisely, I guess we should actually say that we have n lattice points, or n cubed. And I'm not exactly sure. Should I have n cubed here? What is the number of atoms? Because earlier we had just n atoms when we were treating one-dimensional system, and I have a feeling that this is actually a variable that does not being generalized when we go to 3D. So in fact, I would say that you should remove this cube here. So we are just dealing with n lattice points in our treatment. But let's say later how we are normalizing, how do we calculate the Debye frequency in order to find out which way it is. Is it n or n cubed? And we are considering a cubic volume of a solid, and let's consider that the length of a solid of the cube is L, so the volume is then L cubed. So L is the side length. And we apply, of course, the periodic boundary conditions. And okay, I will just briefly mention that, okay, why I have this footnote here, that we're actually integrating over the lattice point. That if you would really end up in a scenario that you would need to generalize this treatment into, for example, a diatomic case or some kind of different lattice where you would really have a different basis of lattice and not just a single atom at the center of the lattice point, then it would be good to remember that we're actually dealing with the lattice points here, that they make the distinction between atom and the lattice point. So we now apply the periodic boundary conditions, and this of course is a condition that on the other side of equality we have the exponent of I kx, and by the way, sorry, I'm missing parentheses here. I should have I in all of these terms, so I should have I kx, I kyy, and I kz here, of course. And because of the periodic boundary conditions, I can move a distance of side length along each of these directions, x, y, and z, and that should be equal to this earlier case. So I should be having equality between x variable when we are in a position x and when we go to a position of x plus L. And similarly, the same way, we have periodic boundary conditions, so they along y direction and along z direction too. And please, my apologies, the I here, of course, we should extend that to all of these terms, so that it's not just that we have a wave propagating in k x direction, we also of course have a wave propagating in ky and kz directions. Otherwise, it would be like a very, very strange attenuating or like amplifying wave that we will be describing here. So this addition of applying periodic boundary conditions here, of course, this is the thing that discretizes our wave vector. And that means that the wave vector components that we have for ki, and now I is either x, y, or z, that extends in a range from minus n times pi over L all the way down to n pi over L. And because we have periodic boundary conditions like these variables, they are discretized. So that's then how things look. And we see that this is the way the periodic boundary conditions in our system now give rise to discretization of the ki values. And here, as we can see, this variable here, like essentially it's an integer of 2 pi over L that is being the kind of step between each k points. So we see that indeed when we are summing over, like we could equally well sum over some integers instead of like summing over kx and ky and kz in the sum over states. and looking at the case that we got the functional form on them, in other way of saying what we see is that a single value of k vector, it really occupies a space that is 2 pi over L cubed. And the k points in the reciprocal space, they are equidistant from each other, and this is really the volume that is being occupied. And now what we want to do is that we want to be able to describe the density of states. So we must somehow see how the total number of states n changes as a function of omega. So that's what we are proceeding next. So we want to somehow find a relation between the number of states n and the frequency. And we note that all the k values, all the wave vector values are really inside a sphere of radius k. And now scalar k, which is essentially the length, the modulus of the vector k that has the maximum value. And the number of modes is n for a given polarization state and phonon branch. And then all of these number of modes, they must be inside this kind of volume. And since each, like a k space, takes a given space, this 2 pi over L cubed, we know that in principle the total number of states can be calculated to be an inverse of the space each k point takes. So L per 2 pi cubed times 4 pi k squared over 3. So this is a way to calculate that how many modes we actually have in this kind of volume of a size of a sphere with a k cubed radius, and then this is the kind of how many points fit there. And now what we can do is that we can now really calculate the density of states. And how do we do that is that we apply the chain rule, and then the density of states, please recall this was defined that this is really the derivative of n over omega. And we have just found a relation for n, and essentially we were finding it as a function of k. So we must now change the variable to omega, and that's where we apply the chain rule. So now we turn this derivative into a derivative with respect to the omega frequency. So this is now what we have. We have the v. So we had the L cubed in our function for n, so that equals v. Then you have k squared divided by 2 pi squared, and then we take use of the chain rule, so we end up with the derivative of dk over d omega. And V here is the L cubed, the volume that the solid takes. So this is essentially just what we had. We had the equation on the previous slide for n, and then we want to change that to be a derivative with respect to the omega, and then we apply the chain rule in order to calculate this. And now we have something like this here, and then we will proceed. So we really now have an equation, or at least some kind of equation for the tensor states. And here we have the term dk over omega. So the derivative of wave vector, or the amplitude of the wave vector with respect to the frequency, this is of course given by the dispersion relation of the system. Like recall, dispersion relation is a function that tells us how does the omega change as a function of k. So now once we know the dispersion relation, we can calculate what is the derivative of k with respect to omega. And this is the kind of key point that Debye solved. That how do you then solve this term, and how do you proceed in then calculating the actual integral. And what we will do next is that we will outline to you what kind of trick Debye used to calculate this term. Because if you remember, in a 3D case, the dispersion relation of a three-dimensional solid doesn't look entirely nice. Or it does look nice, but they not very, very, very easy if we would want to analytically somehow calculate things, because in 3D case the dispersion relations they look not like entirely linear functions anymore. So let's now look how things look in a real case, and let's consider, for example, the dispersion relation of some material, for example, diamond. One student of mine says that I have a serious issue with diamond, that somehow I have a fixation on this material, that I want to always somehow apply diamond into our research whenever possible. And of course I strongly disagree. I don't have a fixation. It's maybe just a fetish on diamond because it's such a cool material. So many songs have been made about diamond, so that I must be right. I'm just joking here. So this is the real 3D dispersion relation, or sorry, let me correct. This is a 1D dispersion relations along certain lines in the 3D dispersion relation of a real material. And we are going from the gamma point, which is the origo of my first Brillouin zone in a 3D case, and I'm here basically drawing a line from the gamma point to the x point, and here I'm plotting the dispersion relation along that specific line. And then I go from the x point to the k point, and these are the critical points of my lattice. And of course, if you would have a different kind of lattice, I would have different critical points, and things would become very, very muddy in terms of understanding on an introductory level. And then from k, we are going back to gamma, and here the system repeats itself. So I'm just plotting gamma over L again here. And we have diamond. When you recall that the diamond formed this special diamond structure, so it was like an FCC lattice, but now instead of a single carbon inside the lattice point, we actually have two carbons, and that gives me a diatomic lattice, and then that gives me a case that we actually have emergence of optical phonon branches here. So these branches here are the optical phonon branches, and these branches of lattice vibrations, phonons that do go into the gamma points, these are the acoustic phonons. So it's always easy to remember and see what happens when you just look at what happens nearby a gamma point. And if you have lines that go into the gamma point here, into the zero energy point, we see that these are the acoustic phonons. And then when we have something here that along this gamma point is not reaching zero energy values, that we have optical phonons, and that implies to us right away that we actually have a lattice that is not just a monatomic, so a diatomic or even more complicated. So in general, when we look a dispersion relation, and what I see here is that the dispersion relation definitely is not a linear function. So I'm not seeing straight lines much in this dispersion relation, but rather I see bends and curves all over the place. And this is just the dispersion relation along certain lines of high symmetry. So this is not even the full 3D case. And this is problematic. So that we somehow would want to have a simpler form for the frequency. Dispersion relation, I mean. And at low temperatures, when we are, if you think what that means in terms of the thermodynamics of our system, when we are at low temperatures, then the kBT values are quite low, and that means that we don't have that much of energy to divide or divide into these different states. So optical phonons, they become frozen out earlier, and when we are at low enough temperatures, we really don't need to care about these higher order phonons, because just according to the equipartition theorem, the energy is equally divided into the different energy states of the system. And if we have a low enough temperature, we don't have that much energy. So these states are really not populated at all. And we only have energy states populated in these lower energy region. And because of this, then it's only the lower energy phonons that matter, that are excited. And essentially, even if we are at room temperature, the kBT value is a 26 millielectron volts, please recall. Then in most of the materials, this is so-called low temperature regime, room temperature. And this implies to us that instead of the full 3D dispersion relation, we only need to consider the dispersion relation omega k near the gamma point. So nearby the region where the k equals 0. So we only need to consider what happens here nearby. And of course, here, like in a 3D case, like the dispersion relation does draw a conical surface, but nevertheless, like here, the curves do start looking like straight lines, and that can be then used to approximate things. So this is the kind of trick Debye was making. So as a good physicist, we always simplify things, and we try to linearize things, and this is also the trick that was being used in Debye model. So now we can really approximate that as long as we are at low enough temperatures, that the frequency, the dispersion relation is really close to a linear function near the gamma points, and this gives us a linear dispersion, and that's quite nice because then the omega versus k functional form is simple. So then we just get that the omega equals v, the velocity of this phonon. So essentially that's the speed of sound in that material times k. So v is the velocity of sound. And this gives us a density of states that we can really easily plug into our integrand, and then we can proceed. So we do not need to care about the actual directions of k vector. We can instead just forget that and assume that things look isotropic. And then we have v times omega squared divided by 2 pi squared times v cubed. So please note here, I have a not very clear distinction between the capital V. So this is the volume, and this is the v as in velocity, so small v cubed. So this is what we have. And with this, equipped with this, we can now proceed to actually calculate the Debye heat capacity and estimate then what is the Debye frequency also. So let's now next calculate the Debye frequency, omega d, and let's then calculate the mean energy, and then let's then calculate the heat capacity. And because the total number of states equals to n, so here we are, so it's not n cubed, but actually n, we can actually form an integral and use that integral to find the Debye frequency. So the total number of states must be equal to an integral from 0 energies to omega d, and then we integrate over the density of states these angular frequencies that we have. And this allows us to calculate omega d, the dpi frequency. Please note that how we end up with this integral is that this is actually like exactly the same thing that we would, for example, use to calculate a mass m of an object. That we would know the shape of the object and the density of the object. So if you have an object and if we know what is its shape, so we know the volume v, we can calculate the mass by just integrating over the density as a function of position inside the object, and we then calculate the volume differential with the density. And this gives us the mass m of an object when we know the shape and density of it. And this is an integral we know maybe not from high school, but at least from the first years in the university. And this is actually exactly the same thing. But now instead of like calculating the mass, we just calculate the total number of states. And here we have our density of states. And here, maybe you also start more appreciating the terminology here. Many times when we're dealing with a term that seems obscure, in fact, when we munch the physics a bit, we realize that the term actually is very correct and accurate. We have been saying that this is density of states. And in fact, looking at this integral, what this d really looks like, it really looks like a density of states. So hence the name for that term. And please, I hope after this you better appreciate the bits and pieces of terminology here. So now we can calculate the integral. I do not show it, but that gives us the dpi frequency, or the cube of the dpi frequency, and that turns out to be 6 times pi squared times the velocity cubed times n over v, where v is the capital V, so that's the volume of our solid we are considering. And now we can actually try to proceed in calculating the mean energy. And that was found to be that the mean energy in the previous slides was 3 times integral over 0 to dpi frequency omega d. And now we can plug in our form for the density of states. So we have v times omega squared divided by 2 pi squared pi times the velocity, speed of sound in the material v cubed. And then we have h bar omega divided by exponent h bar omega per kpt minus 1. And now we integrate over the frequencies. And how this can be simplified further, like we make a change of variables. So we use an xt variable that we defined to be h bar omega d divided by kpt. And we can further define that this is actually theta, dpi temperature divided by T. So essentially we have a variable that we will integrate over X, and that is h bar omega divided by kpt. And that helps us to simplify our integral slightly. So we have the mean energy equals 3 times the volume of the solid V times kpt to the power of 4 times temperature to the power of 4 divided by 2 pi squared times v cubed, the speed of sound in the solid, times h bar time cubed. And we integrate now variable x from 0 to xt variable, and here we have a relatively transparent integrand now. So we have x cubed divided by ex minus 1. So this follows from a straightforward change of variables in our integral, and we can further clean this up by then using the dpi temperature theta term here, so that we can simplify what we have here. So the parameter theta, as in the xt, that was defined to be theta over t. That's known as the dpi temperature, and explicitly that can be given to be a form of h bar times v divided by kpt, and then we have the cube root of 6 pi squared times n, the number of states in our volume, divided by v, the volume of our system. And with this, the earlier integral can be cleaned into a quite neat form. So now we get a final relation for the mean energy. So that's 9 times n times kBt. And then we have temperature T over this dpi temperature theta to the power of 3. And then we integrate from 0 to xt, the variable x. And the integrand is x cubed divided by exponent x minus 1. And this then can be readily integrated, and that gives us the heat capacity C, because then we can calculate the partial derivative of the mean energy with as a function of T, so that we can actually calculate the heat capacity. And the differentiation of the mean energy with respect to the temperature, we can perform that by using the chain rule. And then finally, we get a heat capacity that will be of the form that we have 9 times n kBt, and then we have the temperature T over the dpi temperature theta to the power of 3, and then we integrate from the x variable from 0 to xt, and then we have inside the integral as an integrand, we have x to the power of 4 times exponent ex divided by ex minus 1 squared. So the integration limit here, just to be clear, that was defined to be h bar omega d. Omega d is the dpi frequency divided by kBt, and that was further defined to be theta over t, where the theta is the dpi temperature. So please note, this depends also on the temperature. So our integration limit xt, it's not explicitly shown in the notation, but yes, it does depend on the temperature. And similarly, the variable of integration x depends on the temperature. So if we go to a different temperature and we want to calculate the heat capacity here, please note that the temperature dependence is also inside the integrand and in the limits, and not just this t cubed dependence. So this is not the simplest form, functional form, as a function of temperature. But this is our final result, and this result is known as the dpi heat capacity. And this is quite nice because it does correctly predict the Dulong-Petit behavior, so that when we go to higher temperatures, we get the right kind of temperature dependence. And also when we go to the lower temperatures, we get the cubic dependence on T, so that the heat capacity C is proportional to the T cubed, which is the low temperature limit that was found to be experimentally to be what happens. So it's this functional form that really gives rise to this quite complicated behavior as a function of temperature. So when we go to the low temperature limit, these integrands don't matter that much, and it's really this term that matters most. And when we go to the higher temperatures, then this whole thing starts to be approaching the 3 times R, so the gas constant value, so 25 joules per mole per Kelvin value, and this is the Dulong-Petit value. So I'm now almost done. I just want to show you what is the functional form of the heat capacity when we plot it as a function of T over theta, and theta was the dpi temperature. So here's a plot from the booklet, and that's showing that at the lower temperatures, we quite correctly get the prediction that the heat capacity is proportional to the T3, and then at the higher temperature limit, I'm now plotting as a function of normalized temperature T over theta. When we go to the higher and higher values, we are approaching the ideal 3R case, and this is known as the Dulong-Petit. R is the ideal gas constant. I guess we physicists usually, instead of R, we use the Na Avogadro number times Kb. So at high temperatures, we have the heat capacity approaching 3R, and in the physicist notation, we have R. Instead of R, we use the Avogadro number times Kb. Sorry, this B should of course be in the index. So this is the Boltzmann constant. So this is what happens. So we nicely get a good agreement, and this was surprising in a way at the time, that how to find this kind of form, and how do even justify how do you get this kind of heat capacity form, and quite nicely we get a good agreement when we go to the low temperatures and high temperatures, and in the midway we're not that much on solid ground. But please remember that we did need to approximate things quite a bit. So in realistic 3D solid, we do actually have a 3D dispersion relation. And here we really approximated our dispersion relation, that we only considered phonons that are of low frequency. So we linearized our dispersion relation in order to calculate the integral. And we totally forgot the fact that we may not always have a isotropic volume in the reciprocal space in the first Brillouin zone, so that the things in more realistic solids become not as simple as this simple model described here. But nevertheless, this is the kind of first model that really started to provide an understanding, and more importantly, it showed that the kind of starting assumptions and main principles that are being used in these calculations, they seem to be quite valid. And for example, this way of thinking that energy is being stored into a piece of a solid lattice by these phonons, by lattice vibrations, and the fact that we need to discretize these phonons, it was quite something at the time, and really it laid the groundwork for further development of quantum mechanics and this approach. So this is what I wanted to say to you regarding heat capacities of the lattice. I hope this was a nice lecture and rewarding to you and useful. And next, what we will do is that we will extend our treatment on thermal properties of the lattice. But now, instead of calculating the heat capacities of lattices, we will look into the thermal conductivities of lattice. But that will be, of course, the next lecture. So I will stop here. I thank you for your time, and please follow with me to the next lecture. Thanks, and bye-bye.